All right, athletes, here's 10.1, systems of linear equations, 2 and 3 variables. So we'll talk about a solution of a system of equations consists of all the values for the variable that are solutions of each equation of the system. What does it mean to solve a system equation? Well, it means to find all the solutions. Sometimes those solutions will be independent and some of those solutions will be dependent, meaning it's an equation that is your solution, not just necessarily numbers. So the difference between consistent and inconsistent systems of equations, well, if a system of an equation has at least one solution, might have many solutions, it is still considered consistent. If a system of equation has no solution, it is considered inconsistent. So when we're thinking about equations of two variables, linear equations, your three possibilities that happen. Think about your equations as lines. Well, to get one solution is when you're going to have two lines that aren't parallel and they're going to cross at exactly one point and you get one solution. The other possibility is that you can have a line given in two different ways and you might have infinite solutions where your solution for a linear equation can still be a line where every point on that line is a solution. It's not, be careful with their different infinities here. Infinity here isn't saying that every answer is a solution, but there is unlimited amount of solutions and they could be defined by equation, let's say like y equals x. That is an infinite amount of solutions, but not every possibility works. And then your third option, your inconsistent possibility, is where you get no solutions. So you have two parallel lines, different points they go through. You're not going to have any points that are the same solution for both of those equations. So you're not going to have no solution that's inconsistent. So moving on to the three variable, and that's really where we're going to live for the most part in college algebra. You should have had plenty of exposure to it, two variables in previous courses, but in college algebra, we're going to focus on three. So your first two types are, if you imagine three variables being planes and not lines. Well, you can have three planes intersect to form one solution. Okay, and that's where we can find an x, y, and a z, and it's an actual point. The other possibility to have a consistent answer, notice A and B are consistent, is that when these planes intersect, you're going to have a solution. There is a place where they all intersect, but that whole solution could be defined as a line, meaning it's dependent, but it's consistent. It has answers to the system. Three, inconsistent systems. Well, there's no solution that works for all three functions. These functions being defined as your blue plane, your red plane, and your purple plane. Or you could have them all being parallel planes. There's not one single point that's going to satisfy those systems. So you're going to have, it's going to be inconsistent with no solutions. All right, so let's look at some examples here. So as a bit of review, when we're solving, we're going to focus on elimination because we're going to parallel the elimination with two variables to solve for three variables. So remember, when you're solving by elimination for a system, you want to line up your x's, and you also want to line up your y's, and you want to push everything over here so they're both in your general form. So what you have to do is you have to multiply one of the rows to eliminate. Usually we try and eliminate x first. So in order to eliminate x, I want to try and multiply by the smallest value here. So here, if I multiply this both sides by -3, That's going to give me the necessarily negative 3x here to eliminate this positive 3x here. So if I multiply, and then I'm going to stack and add here. So I have 3x minus 4y equals 4. I get negative 3x plus 9y equals negative 3 halves. So as I stack and add these, hence why it's called eliminations, my x's are going to be eliminated. And I'm going to be left with 5y is equal to, well, this is equal to halves. So 8 halves minus negative 3 halves is going to be 5 halves. Okay, and I can now I have one single variable, and I can just go ahead and solve that for y, and I get y is equal to 1 half. All right, once I get this value, I can plug it into either one of the equations and solve for my x value. So let's say if I put it into my bottom one, I'm going to have x minus 3 times 1 half equals 1 half. I get x minus 3 halves equals 1 half. I add 3 halves to both sides, and I get x is equal to 4 halves, or 2. So my solution is 2 1 half. And I always like to try and check my solution, maybe plugging it back into my first equation, since I use my second equation to solve. And I get 3 times 2 minus 4 times 1 half. And I get 6 minus 2 equals 4. Verified. That's the same as that. And verified my solution there. All right. So with those two variables, notice I've added these two variables. I want to first put them into standard form, and I'm going to get 2x plus y is equal to 4, and I get negative 6x minus 3y equals negative 12. So with these equations, if I was trying to eliminate this, I'm thinking if I can get this top one to be a positive 6x, my x's are going to be eliminated. So that's going to require multiplying this whole thing by 3. When I do so, I get 6x plus 3y equals 12, and I set it up to eliminate, and I notice that they're just opposites of each other. So when you eliminate things, you're going to get something like 0 equals 0. Well, this is true. If I know it's true, it's going to be consistent. Okay? But if it's false, it's going to be inconsistent. There's not going to be any solutions. They're parallel lines. But now that it's a true and it's a consistent solution, that means really what we have is we have two of the same exact lines. This information is no more valuable than this information. They're telling us the same exact relationship. So really the equations are the same. Okay, if you just multiply by a factor, notice if I would have multiplied this by negative 1 here on this side and negative 1 here on this side, I get this equation. So the graph of this system is just going to be one line on top of another line. They're the same exact line. So because of that, our final solution is dependent, and I can just pick one of the equations. The solution to this is 2x plus y equals 4. It's dependent upon a variable. So I have to put in an x, and then I get a y. So it's dependent. It does have a solution. It just has lots of them. Okay. All right, so now 3 variables. So just like we did before, we're going to want to step through this, and we're going to want to try and eliminate x first. Well, let's first eliminate x dealing with these two equations. So to do so, I'm going to multiply the top one by negative 4 to match up with this 4x. So I'm going to get negative 4x minus 4y. Negative times a negative is plus 4z equals 4. So at this point, since I have that, okay, I'm going to add it to my 4x minus 3y plus 2z, and that's just coming from here. And this is coming from, I multiplied it times -4, and that's what I got here. So now when I stack this up, I'm going to get -7y plus 6z. This was 16 here, so this is equal to 20. So I want to do the similar ideas here, but now I want to do it with the bottom two. So I'm going to go ahead and kind of eliminate this. So I just kind of clean that up, and I want to eliminate now the second one. And I'm still going to use the first one to eliminate that. So I'm going to multiply this one by -2, and then I'm going to get -2x minus 2y plus 2z equals 2, and I'm going to add it to this one. So we get 2x minus 2y minus 3z equals 5. So as I add this up, what I'm going to see is that my 2's will eliminate. I get -4y minus z equals 7. And I have that dependent solution. So what's nice now is I look at this one. I have a equation with two unknowns, y and z. I have this green equation with two unknowns, y and z. So now I'm going to treat this like a two-variable elimination using these two. So I have -7y plus 6z equals 20. And I have -4y minus z equals 7. So here, because I have -7y and -4y, I could multiply the top by a 4, and I could multiply the bottom by -7, and I'm going to deal with real large numbers. I'm going to recognize right here I have 6z, and here I have -1z, and the ones are always a little bit easier to work with, so I'm going to eliminate actually my z's here instead of my y's. So multiply this one by 6, so I get that desired -6z here to eliminate from the top one. So when I do this, I have the top equation, -7y plus 6z equals 20, and the bottom equation times 6, so -24y minus 6z equals 42. This should eliminate, and I get -31y is equal to 62. Now I can just divide this by -31, and I get y is equal to -2. So I went ahead and just cleaned this up a little bit here. So now that I have one solution, y equals -2, I can go back into the equations that I had two potential solutions, and I can solve for my other variable. It doesn't matter which one I do, I should get the same solution. So let's go ahead and use this red equation. So I let y equal -2, so I get -7, y being -2, just a substitution there, plus 6 times z is equal to 20. I should be able to solve this and get a solution for z. So I get 42 plus 6z equals 20, minus 42 from both sides, minus 42 from both sides. I'm sorry, this is not 42, this is 14. So I minus 14 from both sides, and I get 6z is equal to 6. Divide both sides by 6, and I get z is equal to 1. Well, I got two answers, but I need 3 because I got 3 variables I'm dealing with. Well, substitute this back into any one of the originals. I like this one. It looks really nice and simple. So I'm going to solve for x. So I leave x in there, plus, well, my y was -2. minus z. Well, my z was 1, and this is equal to negative 1. So I get x minus 3 equals negative 1. So x is equal to plus 3. I get x is equal to 2. I always like to try and check my solutions. So to check here, since I use this equation to solve, check my solution, I'm just going to pick one of the last two. Bottom one has a smaller number, so I'm going to do 2 times my x, which was 2, minus 2 times my y, which is 1, minus 3 times my z, which was 1. Oh, here my y should be negative 2. Okay, so I plugged in my x value, my y value, my z value, and I get 4 plus 4 minus 3, and that's equal to 5, which matches up with what it should be. So I verified my solution. So let's look at another example here. So I'm missing some variables here in each equation, but it doesn't mean I can't solve this system. Yes, there's x, y, and z between the three equations, but not one equation has all three, but we can still go through the same process. So again, I'm going to try and eliminate my x's. So I'm just going to multiply this one and this one by negative 2, and I'm going to get negative 2x plus 2y equals negative 12, and I'm going to get 2x, and I don't have any 0y, so sometimes it's nice to put a plus 0y there, and then I get a minus 3z is equal to 16. So when I add these up, I'm going to get 2y minus 3z equals 0. It's not 0, sorry. Negative 2 times 6 is negative 12, plus 16, and I get 4. So once I have that equation, I'm going to try and eliminate x from the other equation. Well, what's nice is x is already eliminated here, so I have two equations. I have this one, and I have 2y plus z equals 4. So to solve this one, now I have just notice that 2y and 2y are the same, so I'm going to multiply one of them by negative 1. So minus 1 here, and I get 2y minus 3z equals 4, minus 2y minus c equals negative 4. And what am I going to get? That goes away. I get minus 4z equals 0, and then divide by negative 4, and I get z is equal to 0. Well, that's nice. I have z. I can plug it into this equation, and I get 2y plus, well, my z is equal to 0, and that's equal to 4. So then I get 2y is equal to 4, y is equal to 2. So I have z and y. Now I need to get x. So I know that x minus y, so my y is 2, is equal to 6 from the first equation. So I get x is equal to 8. Well, I can go ahead and substitute these back in. Let's try the second one. I plug it in here. I get 2 times 8 minus 3 times 0. What's that equal to? I get 16 minus 0 equal to 16. Check, verified my solution. So number 3, let's look at what can happen if you solve a system out and it's not a independent answer. So first, again, I'm going to try and eliminate x. I'm going to work with the first two equations, eliminate x on that one, and then I'll probably use equations 1 and equation 3 and eliminate x on that one. So multiply the top one by negative 2 so I can eliminate my x. So I'm going to get negative 2x plus 4y plus 2z equals negative 16. I add it to 2x minus 3y plus c equals 23. And I get the equation y plus 3z equals 7. Okay, so I'm going to save that side, and then I'm going to go ahead and get my green one. The first one eliminated from that. So multiply the top equation by -4. So I'm going to have negative 4x plus 8y plus 4z equals negative 32. And then the third equation, 4x minus 5y plus 5z equals 53. So my x's are going to eliminate, and I'm going to get 3y plus 9z equals 21. Well, if you look at this equation, the first two equations, and I want to try and eliminate these, I'm going to multiply this one by -3. So notice I get negative 3y minus 9z equals negative 21. They're opposite equations. I add them up. I'm going to get 0 is equal to 0. Again, it's a true statement, so I know it's consistent, but it is dependent. So to give my dependent solutions, I want to write an equation for y in terms of z. Well, let's just use this one right here. I can say that y is equal to 7 minus 3z. So y is equal to 7 minus 3z. So now what I need to do is I need to write an equation for x in terms of z. So I look at my first equation. I can use any one, but the first one seems nicest, and I can do x minus 2. Well, I don't want to write a y. I want it in terms of z. Well, luckily in my previous problem, I know what y is in terms of z. So it's equal to 7 minus 3z. And then I do a minus z. It's equal to 8. So this is all coming from this equation here. And this piece is coming from what my y was equal to. So then from here is just simplifying and getting x by itself. So I get x minus 14 plus 6z minus z equals 8. And moving some things around, I'm going to get x is equal to 22 minus 5z. So I have x in terms of z, so x is equal to 22 minus 5z. So if z was 0, so if I have ordered pair, usually it goes x, comma y, comma z. If z is 0, what are my answers? Well, if I plug in 0 here for x, I get 22 minus 0, which is just 22 for my x. And my y, I plug in 0, and I get y is 7. So that's a point that satisfies this equation, but there'd be infinite amount of points because I can let z be equal to whatever. So it's a dependent solution. What does this solution look like if we were thinking about a three-dimensional plane? Well, it's a entire line. If you wanted to write your solution out, you would say x is equal to 22 minus 5z. Your y is equal to 7 minus 3z. And then your z, you can just say is equal to z because it is dependent on one of the variables. We could write these solutions dependent upon x, dependent upon y. They look a little bit different, but it's all representing the same line grouping of solutions in a three-dimensional plane. That concludes our notes tonight. Go ahead and highlight any questions and bring them to class tomorrow.